Good afternoon. Yes, I will be building it, but I think there'll be a lot of people that are going to be assisting me build it because it's quite a complex project. Unlike sort of your normal tidal stream projects, it's really a multifaceted project. As Johan said, I'm the project manager that will be looking after the marine and civil works, and really what that is, it's everything except the turbines. And we build everything that the turbines need to operate and be housed in. What I'm going to talk about this afternoon is I'm really just going to take you through what we've done over the last year while the Henry review is being underway. We've used that time to optimize our sort of construction program, come up with a couple of ideas to sort of more efficiently construct it. So I'll talk through that. I can't talk through everything in the limited time we have, but what I'm going to do is really focus on a couple of the key aspects where we've managed to shorten the program and build it more efficiently. I think some of you were on the site visit yesterday. You were very brave in the cold, wet weather. And I really hope the next time we have one of these, when we do the site visit, we'll actually be taking you out onto the site itself and showing you what we've achieved. So what I'm going to be covering, there we go. I'm going to really just recap what the project is. I think a lot of you, certainly you the Survivor group, probably know a lot about the project already. I'm going to just briefly touch on what the various work packages are. I'm going to talk a little bit about our target construction program, and I do emphasize that when I say our target construction program, that is Tidal Lagoon Power's target construction program, and likewise with the construction methodology, that is our reference design. I'm going to talk about DFMA construction. If you don't know what that means, don't worry, I will explain it a little bit later through the talk. And then a couple of fun slides just to really give the project a sense of scale, because I think a lot of people actually don't really understand the scale of the project. All right, just a little bit of a recap on the project. It encloses an area of about 11 square kilometers at high tide. We've got the seawall lengths. You can call them a bund wall, you can call them a dike, you can call them a breakwater. All of those are technically correct. We just call them a seawall. That's roughly about 9.5 kilometers long. We've got 16 20 megawatt bulb turbines, which generate 320 megawatts at peak generation. And we've got 8 sluice gates to allow water in and out at the beginning and end of tide cycles. And our target is to generate more than 530 gigawatt hours per annum from the turbines. And then also we are developing some boating and recreational facilities that will be associated with the project. All right, so that's really just the layout of where everything fits. In the southwest corner, you've got the turbine and sluice structures, approximately 2 kilometers offshore. If you're wondering why it's sited there and nowhere else, the reason is there's a natural deep channel there, and we're making use of that because the turbines need to be down quite deep for them to function properly. We've got the western and eastern seawalls. They really form the impoundment, dam, rock pool, whatever you want to call it. We've got the boating and recreational facility for the swimming, the sailing, with some environmental enhancement associated with it. We've also got, in the corner down there, we'll be creating a salt marsh. And then in that corner over there, we'll be creating a sand dune with a grassland system. All right, really the work packages. Essentially, there are 3 main work packages. It's the civil works, which part of that is you've got your main civil works, your ancillary civil works, you've got your marine works, and in that you've got your permanent seawalls, and then you've got the temporary cofferdam in which we build the structures, and then lastly, but most importantly, actually, are the turbines, because they're the actual thing that generate the electricity. You've got the turbines, and associated with that, although not part of the main contract works, we've got the turbine manufacturing plant. Okay, so really what the main civil works are, you've got the sluice structure. The reason we have sluices is at the end of a tide cycle, you can't generate power anymore. The head difference is, or the water level difference isn't enough. So you open the sluice gates, and that allows the water to level out or equalize very quickly. So we've got 8 sluice gates. We've got the eastern and western wing walls, and their function in life, they where the 2 sea walls join into the structure. And then we've got the dividing structure, and that's quite an important structure from a hydraulic point of view because that leads the water into the turbines. Now, where we're a little bit different to a conventional run-of-river turbine plant is a run-of-river, the water's coming in a straight line. We don't come in a straight line. It varies all the time depending on currents, depending on tides, depending on sea states. So what we've got to try and do is get a best fit to channel the water in as efficiently as possible, and that's where that dividing structure is actually critically important, bringing it in. efficiently. And then arguably the most important piece of the civil structure is the turbine structure itself, and that's the building where the turbines are housed and all of the balance of plant is housed. The ancillary civil works, that's really all of the miscellaneous civil works. That's your site establishment, your roads on top of the bund, your salt marsh and dune habitat creation, and then the sort of marina and the boating facilities that are associated with. I mean, broadly put, it's everything outside of the sort of cofferdam where the main civil works is built. In terms of the permanent seawalls, a fairly conventional sort of rubble mound breakwater, for want of a better word. The only difference between this and a conventional sort of one you would see on a port is we don't want this to be permeable. So we have got quite stringent permeability requirements because it's no good building this thing and then all the water just seeps out through the wall instead of through the turbines. One way of achieving that is you have a fairly dense sand core, which is fairly impermeable. Obviously it is permeable, but very low permeability. Armored on the inside and outside. The inside, smaller rock, you don't have as big a waves, and then on the outside, a bigger rock to protect it from the waves. The two pictures at the bottom really just show, a conventional land-based approach to building a bund wall, and then the picture on the right is probably not dissimilar to sort of what the length and what our western wing wall would look like. Sorry, not wing wall, seawall. Okay, and then the temporary cofferdam. This, to me, is the most critical bit of engineering. What we're really building here is a hole in the sea. The bottom of the cofferdam is at about minus 18 chart datum. So if you think about the tide level going up to about plus 12, that's really around about a 30-meter difference in water level. Incredibly critical piece of engineering. If that fails, it's catastrophic if you're busy working within the cofferdam. So that comprises of a temporary seawall. You've got the dewatered cofferdam itself. And then also there's a marine offloading facility. And the importance of having the marine offloading facility is if you actually don't get your western bund wall connected to the shore quickly enough, you can't start any work in the cofferdam. So that removes that dependency. And then that's just a picture of a cofferdam that was used at Shiwa in South Korea, not terribly dissimilar to what we'll be using. The turbines, the type of turbine we're using, it's called, it's a bulb turbine, multi-directional, triple regulated. Please don't ask me what triple regulated means. I've never really understood it. That the mechanical turbine guys understand. But nonetheless, it's a 7.2 meter diameter turbine, and what the 7.2 meter refers to is really the propeller, or as they prefer to call it, the runner diameter. And then equally important, you've got the two sluice gates. They weigh at about 140 tons each, with those dimensions as shown. They need to open very quickly. So that entire structure we open in about 3 minutes. We get all 8 sluice gates open in 3 minutes to get the water out as quickly as possible. The turbine manufacturing plant, as I said, not directly part of the scope, but a very important part. And this will be developed within the port of Swansea. And the purpose of this building, it's really around the machining and assembly, or the base assembly of a lot of the components for the turbines that are then put on trucks or low beds, taken down and assembled within the cofferdam. All right, our target construction program, I'm not going to run through that line by line, but I think the critical things to pick up are that after about 3 and a bit years, we want to start getting water through the first turbine so we can start our wet commissioning and start finalizing we can then get the rest of them commissioned after about 4 and a bit years. Okay, very briefly, I'm going to run through DFMA, what DFMA construction is. It's designed for manufacture and assembly. I think, because I have to speed up, I'm not going to read through that, but it's really just building something out of precast. Now, the reason we've gone for this is it reduces your time. You can start your civil works in parallel with your marine works. You don't have to wait for the dewatered cofferdam. It allows us to commission the project earlier and get water through earlier. Very important, there's less vehicular movements into the bund, which is a lot safer. It simplifies your construction. And the biggest benefit of this is on the turbine substructure, which is what I'm going to focus on. So really, that's the turbine substructure. If you strip that out of the whole civil works, it's a block that's about 210 by 70 by 17 meters high. Its cost contribution is about 52% of the cost of all of the civil works. But more importantly, it's actually the critical path runs through it, because until that's done, or partially complete, you can't put your turbines in. So what we've done is we've developed this system of building it because you've got a very complex shape in the draft tube, which is dictated by the hydraulics required for the turbine. And you can see there, that's your temporary formwork. If you went the conventional route, very complex, very time-consuming. So what we've come up with is this modularized method of construction. And from this, we've determined our target construction program. And that's really taking it, breaking it into simple components. The light gray is precast off-site, and then the dark gray is in situ or site poured concrete. So we've sort of balanced that we can build it as quickly as possible. I think because of time, I was very quickly going to run through this. I won't talk through each element, but you can actually just, if you follow the light gray concrete, you can see how a typical turbine tube gets built. Here, we can get in very quickly. We're putting in the draft tube liner, which is a steel liner because the velocities are so high as it goes through that particular section of the draft tube, it will actually erode the concrete away. Okay, we then build the walls, and now you can actually get in there and you can start putting your bits of your turbine in using the crane. And then you finish it with the concrete. Really what we call it, it's like a static production line. Because instead of trying to build everything, what you're doing is you're working along a face. And as you can see there, you're busy building walls on the right while you're putting turbines on the left. So you work your way along until such time as you've finished all 16 and you've got a watertight structure. Your sluices don't need to be watertight because they allow water in and out. Now once you've got that, to allow us to take that cofferdam away and get water through for the wet commissioning, we're going to employ what's called a limpet cofferdam, which looks like that. It's those blue things over there. And it's just that. It's like a limpet. It sticks on the outside of where the draft tube is, stops the water getting in. So we can then, the civil guys, can start doing the scour protection, removal of the cofferdam on the outside, while the turbine guys are still installing the turbine on the inside behind these stop logs. They're quite happy to do it. They're quite used to doing it. Then, just really to give a kind of a sense of a scale, you all know the stadium that we're in now. Well, if I put it next to the structure, that's what it would look like at the same scale. So it just sort of gives you a perspective of what the project is. If you put some rugby fields at the bottom of the cofferdam, you'll fit 7 rugby fields, and it'll have some space for some stands of people. So again, it's a fairly big cofferdam at the bottom. And then the amount of concrete that goes into the structure, and I apologize for that bit that crept in at the top. If you took your normal 6 cubic meter wagon that you're used to seeing driving around the streets here and you park them bumper to bumper, they're going to stretch for about 300 miles or as far as I don't know where that top bit goes to. But that's how far they would stretch if you park them bumper to bumper. Thank you. Did I make it in time?